Okay, cool. So if you know any of your friends who are not in the class yet, please let me know. Otherwise, I'm going to proceed and keep going. The video will be posted on YouTube, so you can watch it later anyway, but it's good to be in the class so that you can ask the questions. Yeah, I know people might be having midterms, but it's the part with responsibility. Uh, so today we will talk about concepts that allows you to move into the topics of parallel programming. So I hope you're excited and uh, basically excited to learn what you can do to make your program faster. And we'll start in Scala and we'll gradually shift to whatever is more common in nowadays programming, which is Rust programming language. I will also try to cover OpenMP as well. So these are some of the example parallel programming framework that allows you to write the program and execute hopefully faster than a single threaded program. When I said hopefully, it doesn't mean that it will guarantee to be faster. Sometimes you write parallel program and it's actually slower. We'll cover that and why that is the case. So when you talk about concurrent asynchronous program, what does it mean for a program to be concurrent, right? By definition, if you look at the English dictionary of the word concurrency, it means that you're running something together. You're doing something together at the same time, right? When a program running concurrently, it means that you have one program or two programs that perform different tasks, right? Inside a program, generally it contains multiple tasks. Some of them will be go through the loop and initialize some of the arrays to 0 to some initial number. The other part of the task would be read, right? Go and read the input. Another set of tasks will be, okay, given the input, can you process the input and write to the output, right? So those are different tasks. If a program can be run concurrently, it means that some of the tasks can be done at the same time. A program to be asynchronous means that there is no synchronization point. What does synchronization mean in English? And this is a question I'm waiting for your answer. Basically, what if you look at the word synchronization, what does it mean? It is somehow connected, right? So let's say you have a group of people. If they are synchronous, it means that they would be whatever they do connected, and they have to go and perform the task together, right? So yeah, that's it happened at the same time. Yeah, that's one way to kind of like quickly summarize it. Asynchronous means that you still try to do something, but it's more chaotic in a sense, right? You don't have to make sure everything would happen together. But that's actually a benefit to asynchronous programming. In functional programming, right? Whatever we talked so far, yeah. So one of the comments like, so is it like a sharing same variable to run? That's one prime example, and I'm gonna cover this topic. Whenever you have a variable that's shared across different tasks, for example, you have a shared linked list, right? So you have linked list, right? Anyone here doesn't know what a linked list is? Because I don't mind explaining what a linked list is. If you don't know, I'm gonna use that the based on the whether you say yes or no. I assume everyone know what is a linked list. So one of the questions you're asking me privately is, would this give us a right to data dependency? They're two separate issues. Data dependency is more on the line of like when you write a program, sometimes one part of the task is producing the data for the next set of tasks, right? It's normal. You process the input that are being processed is moved to the second phase of the program. Sometimes that causes data dependency, and it can reduce the performance of your parallel program. In a functional programming model, let's say you have let's just go back to the discussion about shared data, right? So let's say you have a shared linked list, something like this, right? What do I do if I want to insert this one to this location, something in the middle? What do I have to do? You change the pointer, right? So basically you make this thing point to this thing point to this, and it get rid of this. Right? Any questions about this process? So let's say there are two threads, right? One and thread two. Okay, let me erase the whole thing because PowerPoint fight me again on drawing. Okay, so if that's your curiosity question, which is faster, typically parallel iteration. That's almost always a lot faster. And I'll tell you why. But let me go through this linked list example. So thread one, thread two. This one want to insert something, which is exactly this, right? And let's say thread two want to read the fourth element. All right. So if I have this shared linked list between these two threads, these threads are basically a part of the same program. One of them want to insert into the fourth element. The second one want to read the fourth element. One thing that can happen is this. The thread one start to modify the list. If you don't lock this linked list, thread one comes in and say, okay, I'm going to make this point here. This thread two, let's say it actually want to read this thing, right? It want to read the fourth element by the fourth element. At that point, it want to read this thing. So it's perform pointer chasing. This process is called pointer chasing. You look at a pointer, you keep going. First element, second element, third element. Okay, what's my pointer? Fourth element. So you read this. Do you see that now it's reading two different things? So this is a problem where you have to perform some synchronization, right? Some synchronization. Asynchronous parallel programming is basically if you detect something like this, when you have sharing, you try to minimize, and when you have parallelism, when you have thread one and thread two, you make sure this case doesn't happen. You are trying to minimize the synchronization point. Now let's go back to the question of which one faster between recursion and iteration. Recursion, what happened is recursion typically have this, right? You have f of n, you call f of n minus 1, you call then f of n minus 2. Well, f of n minus 2, right? So what does this mean? You need to finish f of n, some part of f of n, before you run f of n minus 1, before you run f of n minus 2. Is that correct? So that's kind of like a normal recursion. Let's break this into a loop, and we do this in parallel. Iteration 0, iteration 1, iteration 2, iteration 3. Assuming that there's no shared data and everything is done in parallel, you can do this at the same time. You can do this at the same time. The way you program it this way, it's actually helped, right? The runtime figure out, okay, this can be done in parallel, so I will process them in parallel. This doesn't mean it's constant time. Constant time means that within the iteration is also constant time. This I don't provide any assumption. So this doesn't mean it's constant time. It just means that this can be done, each iteration can be done in parallel. How much time it takes depends on each individual iteration. All right. So hopefully that's clear. It's not constant time for sure, but you can figure out how long it would take within the iteration. And this is going to be faster, hopefully, for each iteration you're processing the data. All right. So let's go through some example. Let's say you want to count the number of occurrence of a list on the web URL. Actually, I don't have the code on Canvas because I figure it might be easier for me to share your code here. So here is the example, right? Let's break this down. Let's break this down one by one. So let's do this as a group exercise. It's not in class exercise. I'm asking you to submit a code or anything, but let's do this as a group exercise. So what I do here, can you see the screen? Okay. So what I do here is I first import in a library that allows me to deal with URL, right? So yes, I can make the font size better for sure. Let's do this. Okay. So I guess it's control and view up. Is it better now? Is it better now? Okay, perfect. All right. So from this code, the first line, nothing much. Right? I just want to get the library to process the URL. It's nothing related to parallel programming or whatsoever. Whatever we want to do is print count, and let's see what count is. Right, let's see what count is. Count is defined as web URL. Oops, I just modify my code. So you have the web URL, you map the URL, and you perform this function call on the URL. So we'll do one at a time. We do one at a time. What is web URL? It's a vector. What is a vector? Let's treat this as an array of 3 strings. The first string is the Mahidol University website. Specifically is the MUIC website. The second website is apache.org. The third website is scalarlanguage.org. Any questions so far? Basically, we have this array that consists of multiple web URL. The second thing we do, basically, we have this URL. So for each of these URL, we count using this function called counter. A counter with the string. Input is a string of URL. The first line doesn't do anything. It just print, hey, this is a website I'm trying to do something with. Okay. The content here, HTTP GET is when you have the library that deal with URL, you can put in the actual URL like www.apache.org, put that inside the HTTP GET function, and you get the HTTP, basically you get the website, the content of the website, right? So when you have the source, right, basically the contents here is the source of that web page, right? The source of that web page. What I do here next is I'm gonna tokenize. What does tokenize do in any programming in general? What does tokenize function typically do? When you have a string, basically, content is the string that is the source of your website. Tokenize means I'm gonna break this string down into multiple chunks, right? Multiple chunks. So you have the URL, you print the URL, you print the source, and then you actually call tokenize up here, which is defined right here, right? What it does, I'm gonna split. Basically, I'm gonna split the content and count the keyword. What is my keyword that I'm counting? It's defined somewhere on this code. So can one of you tell me what line tell me the keyword. I'm trying to count. Yes, so you got it. So one of you answer the THE, right? Why is that the case? Count keyword take two inputs, right? The first input is the string called keyword. The second input is sequence of string. Why is this a sequence of string? I have the URL. I have the source code of my website. Why is this becoming a sequence of string rather than a string? Because you tokenize it, basically. Yeah, because the output of this line give you a sequence of string that you can count later, right? And you put tokens in here. You want to search the website for these words. You want to search the source of the website for the occurrence of the word the. And you want to see how many times that word appears on each website. Okay? How many words appear on each website? Any questions so far? The HTTP GET function, okay, so first of all, the first question is, can I go to the counter function again? I'll do that later because the second question is a lot easier. HTTP GET function is a function that if I give you my URL, I got the source code of that web page. If I give the HTTP URL format like http://www.apache.org to the input, I will get that web page source. Will it read Thai language? I think so. Because it's a string, right? So I think you will get binary that represent the string. But I have not tried it. I'm pretty sure that mahidol.ac.th has the Thai version. So I think this also should work on the Thai language. I'm not 100% sure. I'm like 95% sure. And yes, the string has a built-in function. No, that's not a built-in function. Oh yeah, my bad. It is. The function called count is a function inside there's a built-in function of a sequence. So if you have a data type sequence here, sequence of anything, you can use sequence.count, which would take the input, it would compare to something. This is the input to the count function. It's a function to do the comparison. If it's true, you count that. If it's false, you don't count it. So that's a built-in function for the sequence. The code just count the frequency of the string you put in across a bunch of websites. Right now, the string is the over here. So I can change the word I'm gonna search and count. I can change it to hi, right? So this will check out for each website how many times this word appear, which almost all the time is gonna be 0 actually. How many times you see the word hi in your in the website. Okay, so the third question, I mean the first question that we have. Does it check for the word or a substring of it? Depends on how you define this function. This is a function that the built-in function count would use. If this function return true, it counts. If it return false, it doesn't count. So you can make this to be more complex, basically. The function takes a function as an it takes it basically true or false as an input. Over here is a function that will give you true or false value. Right? So whatever, depending on how you want to build this comparator, like the way you compare, you can actually make it more complicated and give true if you want to just look at a substring inside my token. So does it answer your question? Okay, so it seems to answer your question. So the counter function is basically I have the source code of the website. I first tokenize it so that the source code is now broken into each word. For each of these words, I'm gonna run the keyword function to compare if the word match the actual text THE. That's all, right? If it does, it's true, you count that. Otherwise, you don't count it. Any more questions on this particular piece of code? Because then we'll proceed on how can we make this faster? So if let's switch back to this and ask this question. Let's see what blocks the call. And I basically the definition of blocking calls are part of the program that has to finish before the next part begins, right? Part of the program that has to finish before the next part of my program begins. My first question is, why is this bad for the performance of the parallel program? And you already got the answer. Yes, the answer is the blocking call is the counter function. Why is this bad? It's basically you need to finish the first time before you finish the second time. There are better way to write this function actually. So if you look at this, right? Are there any dependency between these three websites? Do I care about what's the output of my Mahidol University counting? The answer is no. And yeah, so the second question, it will run according to the priority with single thread. Yes, the OS, the way, so I'm gonna go side topic here because the question is a little bit toward the how the OS work, right? If you look at your code, actually, let me open up a task manager. If there's here, okay. Nope, it doesn't show the priority of my task. But let me use Linux. Give me 1 second. I'm going to show you the exact things that you're asking. Okay, I cannot connect to the internet, but on this on the system. So can you trust me on this? Basically, in Linux, each program are given different priority. Some of them will be low priority, some of them is medium priority, some of them will be high priority. Based on that, the OS, the OS, there is a part that there's a code built into the OS, and you can modify this. If you want to hack the kernel, feel free to go in and modify this priority. But what it does is it looks at the priority value, low, medium, and high, and it will perform scheduling. Which one should go first? Which one should be scheduled later? That's a great question. Is it safe? Generally, yeah. Generally, this is safe because scheduling means that it just gives you the order of which task gets scheduled first. Eventually, everything will be finished, right? If we assume unlimited amount of time, eventually all the tasks that you have will eventually be finished. Is that fair? Yes. Is it good? Depend on how you modify it. There's actually quite a lot of papers, even now, even today, that talks about how you should change the policy to make certain things faster. For example, I'm gonna if you in my class, this is one of the example I'm gonna give all the time. Let's say you have a self-driving car, right? So you have heard about this technology. It's been out there for a while, in a kind of like research, and hopefully the company can roll out self-driving cars soon, right? What it does is there's a lot of sensors around the car. Those sensor detects the environment around you. It builds the map. It's a 3D map that corresponds to everything around you. There's a tree right there that are 5 meters from you. There's another car right there. It's 3 meters from you. In the next 2 seconds, that car is maybe 3.5 meters from you because that car is faster, right? Those map building is probably high priority, right? Why? You want to make sure the car can see things. Otherwise, you're driving blind. What's the risk of having a car that driving blind? It's pretty high, right? You can kill someone because you don't see there's a person crossing the street. If you deal with this priority properly, it means that you can guarantee if there's someone crossing the street, there's actually work that try to provide these kind of guarantee that you can detect that human within certain amount of time, within maybe 1 or 2 milliseconds, within one tenth millisecond, so that you can start to brake, right? So in the context of your question is it safe? Depending on how you fix it and depending on how important is the task. In the area we call embedded system, there's a concept called deadlines. There's a hard deadline, there's a soft deadline, and there's a task with no deadline. Can you give me an example of a soft deadline we have in this class? I'll give you one example. Our in class, yes, exactly, yes. That's a soft deadline, right? I put in the due date and I realized I recommend you to finish it by those times and it's okay. But if you don't hit that deadline, no one dies. How about the hard deadline? The assignments, right? So if you miss that deadline, there is some pretty severe consequences, which means that you don't get the assignments grade, which can be pretty severe. You can fail the class, right? In reality, this hard deadline is actually more and more, actually more severe. So the assignment is more like a soft deadline. It's bad. Soft deadline is like it's bad, but no one dies. Hard deadline is bad and something crash. For example, if you miss some of the hard deadline in the OS, your computer would crash, right? One like hardware related hard deadline I can tell you is we all know the DRAM that you buy, right, and put it in the motherboard, the memory that you buy. So that memory, how many of you realize that they actually consist of capacitor? The capacitor that you use in like the front camera of the car, the what I forgot what it's called. Wait, I should not forget that word. It's a camera you put in front of your car windows to actually record the video of when you're driving in case there's an accident so you can replay it later. That camera, they use capacitor. So in DRAM, they actually use the same thing. It's a capacitor that stores your data. What is the property of capacitor? What happens when you keep it on? It loses charges. It means that electrons actually slowly leak out. Electrons actually move out of the capacitor, right? Which means that whenever you have the DRAM, it means that you have to rewrite the data that you have every certain amount of time. Actually, that's the opposite of flash drive. So if you're curious, now I'm gonna go super sidetracked. Just because I just because I work on this area, so I can tell you what happened. Uh, so we'll go to flash drive later. But the way DRAM store your data is they put electron in the capacitor and you have to rewrite that every 64 milliseconds. There's a time limit. If you don't rewrite that in 64 milliseconds, you cannot have a guarantee your data stays there. The bit that represents 1 can be flipped to 0. The bit that represents 0 can be flipped back to 1, depending on how you store the electrons. And depending on whether you would say, if that's electron, it's 1. Sometimes some DRAM say, if that's an electron, that's a 0. But basically, you can see that the bit can flip. What happened when your bit flip? Your data change. And your data change. So how many of you have a blue screen that say memory corrupt? Like something like memory corruption? That's a part of it's potentially, it might be because of this thing. DRAM are failing to basically write the data on the cell. So your bit flip. When the bit flip, the OS say, hey, that was not the data that I saw earlier. Something changed. Something has to be corrupting the memory. So I'm gonna crash myself and reboot because someone might be hacking my system, right? It's the same exact behavior as someone hacking to my system and change the data. So the OS will say, to be safe, I'm gonna reboot myself, right? So that's one thing that can happen. The more common thing is because because I know how it works is uh, inside your DRAM there's a chip, there's a small chip that control this thing. So most of the time this will not happen, but it consume energy and make your DRAM slower. What actually happens when you have the blue screen? So what's more common? Then you might be surprised about this. You know that when you're around the sunlight, right? And sunlight has like gamma particles, beta particles, the things that can energize your molecules. Go back to chemistry, right? When you have energy hitting your atom, the state of your electron go up, right? Between certain energy state to a different energy state. When you have this thing hitting your capacitor, the same thing happen. The electron gets energized and it bounces out the capacitor. There are actually papers that study this, right? And provide some data about like, okay, if you are on a plane, there might be more likelihood because you are actually in the upper atmosphere. So there are more like gamma and beta particle in that level of the atmosphere. So you are actually more likely that your machine reboot because of this. So that's actually one of the possible reason why DRAM is corrupt. Another reason is, well, the cell leaks, right? It actually, these things gets older over time, right? Think of it this way. Every time you put charge in, it's like you shock the cell. So how many times you get shocked and you survive, right? Think of it that way. So the more the cell age, right? The more the cell age, the less likely that they have the same properties as when they're born. So sometimes they just lose charge because that cell is older. There's also a study that when you manufacture DRAM, some cells are actually more, we call it weaker. Weaker means that the electron tends to leave that cell a lot faster. Right? So hopefully you find this interesting. That's DRAM. So now let me go to SSD. Again, super sidetracked. The way SSD work, you don't store electrons. You store actually a state of certain things. Uh, for example, one of the technology is you shock the cell. Oh, okay. So let me get back to that question later. But in SSD, right, we call this non-volatile memory. So what does volatile mean in English? This word. What does volatile mean in English as a by definition? All right. If you don't know it, someone Google and tell me what does it mean. Because this actually goes and apply to both DRAM and SSD, and everything would make sense if you know what that word means. It can change rapidly or unpredictably, right? DRAM is a volatile memory. As I said, electron leaks out. It changed. It changed the state. So we call DRAM volatile memory because of the property of the physics. Non-volatile memory are SSD, right? Hard drive. So these days, there's actually full-blown like non-volatile memory that can replace DRAM. What it does is, so I'll give you one example of the technology called phase change memory, right? It's built from, instead of capacitor, it's built from what we call chalcogenide material, and that material hold resistance. But when you shock that thing with different voltage, the resistance change. So based on the value of that resistance, it can be 1, 0, 2, or 3. Basically, you can break it down into 4 different chunks. And if it read this much resistance, it represent the value 0. This thing represent the value 1. And because this thing doesn't hold electrons, nothing changed. So you don't have to, basically you don't have to refresh or rewrite the data, right? So SSD, if you store the data stays there. You don't have to keep writing. So you got the idea, right? Why SSD doesn't require writing it again and again and again to maintain the data. That's why when you basically power off the machine, your data in the SSD stay there. All your files stays there. When you power off the machine, it means there's no power. There's no way you can rewrite anything, right? Your data stays there. What is the downside of chocking that thing all the time? What's the downside? What happened if I'll tell you I'm gonna keep shocking you all the time. Whenever I write something, I'm gonna put in different in voltage, there'll be electron going through your body. You might die. Yes. So you might have heard that if you buy the SSD, they have certain lifetime, right? 5 years is the average lifetime of an SSD. The reason behind that is every time you write to an SSD, it slowly die. As uh, as bad as that sound, that's the truth. When you write to an SSD, it's slowly dying. And you might have noticed in SSD, when you want to buy a 256 gigabyte SSD, so you actually only get roughly 240. How many of you realize this? You don't get all the capacitor that they claim. When you boot it up, it's not 256. How many of you notice that? Or you, yeah. If you notice that, the reason behind that is those 16 gigabytes is actually a spare part that if certain cell die, that data would get remapped to this spare part. It's actually as simple as that, right? There's actually again a chip inside the SSD that takes care of that. It will provide the mapping, and you say, okay, this cell has been written over 100 and 1,000 times already. That cell is about to die. I'm gonna move that data to somewhere else that I have as a spare part. Uh, I, I have something in mind I was about to say about the SSD actually. But regardless, if you're curious about this, let me know. I know quite a few about these things, and I would not mind at all sharing. Uh, but yeah, let's come back to our slides. Let's come back to our slide. I don't even notice how we got so sidetracked and discussed like all those things. So let's come back to the blocking calls, right? Oh, I know how. We start from priority in the OS. Okay, let's come back to the blocking call. You have a task. Task one depends on task two, and task two depends on task three. The bad things about that is these are sequential. How many of you heard about this word called Amdahl's law? Okay, so here's the content of Amdahl's law. If you want to get performance through parallel programming, you better design the algorithm so that it contains a lot of parallel parts. Otherwise, the serial portion of your code limit the performance. I'll show you the figure, right? And not the data figure, but it's more like a drawing of what I mean. It basically trying to tell Gene Amdahl are trying to tell everyone, if you want to buy multi-core CPU, make sure your program can run in parallel. Otherwise, you don't get the benefit. The serial portion of the code becomes the critical performance bottleneck in parallel program. And here's a paper. Notice how old that paper is. People have been thinking about parallel programming back in the days. Right? multi-core has been there for a while. When I talk about the word critical section right here, it means that it's a part of the program that require either synchronization. Remember the shared linked list as an example where you have to lock the linked list, or you need to resolve some contention. It means that only one, sorry, only one task can finish at a time. So critical section generally can be broken down into two cases, right? This is one of the possibility. Both of these are sequential part or what we call critical section. Even though you parallelize the code here, you have the barrier. We call this barrier. What is barrier? Barrier means that everyone has to wait until everyone finish so that you can proceed through your code, right? So that's the critical section. The really major part of the critical section is right here, right? You notice you have 7 things that you can do in parallel, but because somehow only one of them is doing something. So how much slower do you expect during that sequential part compared to the parallel parts? There are 7 parallel threads, right? Over there, you only got 1/7 of the work done because only one thing is doing something. So right now, you have to a little bit think of it this way. Don't think of things as O of the big O anymore. Big O tells you what's the scalability. Like if you keep increasing the size of your input, how much work do I have to do? We talk about the span. The spans mean that given all the work I have to do, how many things I can do in parallel. We actually will talk about span in the next lecture, so keep bear with me. We'll definitely formally define that. But yeah, so let's say you have a processor that has 8 CPU, right? 8 core processor. Look at this thing. It means that at maximum, only 7 of them will be power up and doing something, right? And there'll be a chunk of time, only one of them will be doing something. Otherwise, the rest are like, I have nothing to do. Right? So you got the idea, right? Why this is slow, or why this can potentially become slow. Yeah, just sit there waiting. Yes, the 8 core CPU, 7 of them are sitting there waiting. Another thing is, let's say you have a shared linked list in this example, right? Let's say this is a shared linked list. And this shaded region, it means that someone want to modify, right? Their linked list. Why do you have to wait? Why do I have to wait? If someone else is modifying my linked list, can someone tell me the reason? So if I modify linked list at the same time, what can happen? Yes, you have to wait and see what the change that they want to make. Otherwise, you get incorrect results, right? Basically, I'm gonna use this example. Let's say I have a bank account, right? Let's say I have a bank account, and somehow there are 2 people, right? There are 2 people that I'm gonna get back to your question later. It's OOE, out of order execution. So yeah, we'll get back to that later, in a bit actually, because I think I need to also give people here some background about architecture, which I don't think if you take architecture with previous semester, I don't think they cover that topic. Uh, if you have a bank account and let's say 2 people want to withdraw the money from an ATM, it just happened to be at the same time. Let's say I can clone myself and clone my ATM card, plug the ATM card into the ATM machines that are at 2 different places. Let's say I have only 500 baht in my bank account. I'm so broke at the moment, right? And I say the first person withdraw 500. The second person also want to withdraw 500. Over here at the bank, like if you are the programmer at the bank who need to program the whole like this ATM system, you have to make sure if someone is doing something with that bank account, you lock it so that no one else can use it. Otherwise, I can manage to withdraw 500 baht twice, even though I only have 500 baht on my bank account. So you need to lock it, and one transaction has to happen at a time. You can't have two concurrent transactions. So you got the idea, right? This type of sequential critical section is coming from shared things. You want to make sure there's no concurrent modification. All right. So if you want to look into this a little bit more, this figure, I got it from the paper called Modeling Critical Section in Amdahl's Law with the multi-core implication. The paper talked about, okay, let's take Amdahl's Law back in the day and apply this to multi-core. This is presented in ISCA 2010. ISCA is like the best conference in architecture. This is one of the work that talk about how you do analysis on program performance. So now I will go back to your questions about out of order execution, which is not exactly related to the content of this class. It's more like how the hardware design works. Basically, in the hardware, if you look at the CPU, it's not actually running your program in the way you program it. The way you run it is the CPU imitate data flow. What data flow is doing is similar to functional programming. Whenever you have the data, you proceed to run it right away. Think currying, right? The currying topics that we talked about last lecture. The CPU is designed in that way. If I have my data, I'm gonna run it and I'll execute some of my function right away, even though it's not in the same order of how you write the code. And yes, so for your question, so you don't run the same code segment twice. Basically, so that you make sure you run the code exactly based on how you program it. Does it answer your question? Basically, you want to make sure you know exactly how this program would behave, and it should behave the same way you program it. So you need to lock it, so you know exactly how the order of things would be executed. All right, so let's talk about how to handle blocking, right? Blocking is bad because it's a task that dependent on the output of another task. So you can do this synchronously, make it serial, serialize that, run the next task afterward. Right? So what are the benefits of this? What are the benefits of blocking? So as a programmer, would that be easier to manage? Yeah, with synchronization, your life as a programmer, even though it sucks, but it sucks a lot less than asynchronous blocking. Yeah, so if you start writing parallel program, you would then realize that your life as a programmer gets a lot more complicated because you need to make sure you lock things properly. But it will be actually at least less complicated than asynchronous program. What are the downside? Potentially, this is bad for performance. So you can do this asynchronously. So while you're waiting for the blocking process, you find something that are not related to the dependent tasks, right? So let's say you have this, you have task one that produce something for task two, and then you have task three. So when you run, this is your CPU, right? You run task one, CPU one, CPU two. You know that T2 depends on T1. So you just basically say, I'm gonna run T3 over here. And then when T1 finish, I can run T2 right here. Okay, so this is called asynchronous parallel program. Is that like a halfway of the two? I would say it's asynchronously is more like an optimization of synchronous parallel program. You look at all the critical section and see if you can make it faster and how, right? So benefit here is faster. Downside, your life is more miserable. You need to basically actively find where's my T3 that I can run, right? That I can run and still benefit from having multiple CPUs. One thing I would like to, what is dreaming? Dreaming? Uh, Not sure. I think it depends on how you program it. Yeah, I'm not sure if you can obtain through dreaming. If you can, yes, congrats. I cannot. Okay, the notion of time is basically traditionally functional programming doesn't focus on the notion of time. There's no serial things anymore, right? Uh, if you look at Scala, there's no state. The fact that there's no state means that I don't care about time. If I have my data, I'm going to run my function. That's all, right? So Scala support is kind of like parallel program. But if you want to have some notion of time, if you want to have some state, some notion of time, Scala support this by what we call the future. What does future mean in English? Okay, I don't even know how you, yeah, it means future. Yeah, so basically future T, it means that eventually whatever I do here will result in the type T, right? And it will eventually becomes available. The value can have multiple states depending on the time we request the value, but eventually it will become type T. And yeah, that's a great definition. Time that is ahead of now. So if you look at this, it means that future can have different states, right? It can be any type, but eventually that will become type T. And generally there are two kind of like conceptually in an abstract way, two states, complete and incomplete. Complete means that all my computation on this future is done. It is type T. Incomplete means that, yeah, I'm still dealing with this data. Eventually that will become type T, but right now it's not. Right? So think about this. This is a kind of like a wrapper that represent that eventually this thing is going to be type T. If the computation goes wrong or time out, it dies. It dies. Someone kill that thread, right? This future becomes an exception, and this is a write once container. Write once container. The unique thing about the write once container is initially it's mutable. You're gonna change these data until it becomes complete. Once this is complete, you write it and becomes immutable. This T is, so that's a great question. Basically, the question is this T a whole program or just a line of it? It's a data. So you can define a data that has future properties. These data will eventually result in the data of type T. So let's do an example using Fibonacci, right? So first of all, you import future so that you can use it. Notice how this is concurrent, right? We start having the concurrency or parallel programming concepts bind to here. So, and kind of like, okay, where Fibonacci is, you can do this, right? Any question about this line? That's basically a typical way to write Fibonacci. Okay, I assume there's no question. Basically, you return fib of n minus 1 plus fib of n minus 2. If you want to use the future, you can define it like this. F1 equal future of fib 45, right? You basically tell the tell scalar that F1 is going to equal fib of 45 in the future. I will start running this now, and I promise that eventually that will be fib of 45. This will take some time, right? Because FIFA 45 is a lot. And you can even do this. You can then, in the next line, say F2 equal future of FIFA 46. Are there any dependency between FIFA 45 and FIFA 46 based on how we define the function? No, right? If you run these two lines back to back, they will both run at the same time, completely in the background. Yeah. It has all the input it needs for the Fibonacci, right? This 45 is known, which means that you can start Fibonacci, right? 45 now. Future just tell that eventually F1 will equal 45. So it actually, yes, it does use a concept of, scalar runtime would use a thread and say, hey, run 45. Eventually that would yield F1. Can we store 45? Yes, this is how we do it right here. That's F1. It just basically we just tell the computer that I need 45 and eventually I'll get it. So if that's a great question. So that's multiple question. Let me do one at a time. So the first question is for F2, is there a case where F2 cannot run? Yes. So let's say if I do this, val F3 equal future of fifth of 7 plus F1. What does that mean? Is F1 dependent, right? It means I need to finish F1 before I can even start F3. So the second question is is there a limit for this future? I guess the limit is how much memory you have in your computer, because when you do these things, basically what can happen is you spawn multiple threads, but you have only say 4-core CPU, right? Which means that some of these threads start to use the CPU core. Some of them are waiting. Is future run in parallel? Yes. So basically, when they are waiting, they have to be stored in the main memory for them to be run in the future, right? So eventually, the hardware will say, "I can't keep up anymore. Let me crash myself." But the limit is pretty high, actually, right? Let me put it this way: if you look at parallel program, Chrome is done that way, right? Google Chrome, how many tabs do you have opening right now? 10? Yeah, it means that you have at least 10 threads running on your machine, right? So the limit is pretty high. You can have hundreds of threads, right? So if you look at Task Manager, for example, you see a bunch of processes, right? Those things, each one of them is one task that actually want to occupy your processor. So if you have 100 lines of those tasks, it means that your processor, the 4-core processor, the 8-core processors can do 4 or 8 at a time. The OS come in and switch that in a really, really high speed so that everything looks like it's done at the same time. And so this is done completely in the background. The limit is how much memory you have. So eventually when memory runs out, they would use the area in your hard drive. Then your computer becomes really slow. Does the task get assigned to a fixed part of the processor? That's actually a great question and depends on the scheduler. Where basically what will happen is when the processor becomes free, it will go and grab the next task to run. So they're not exactly assigned a fixed processor, but it's more like they will go and seek out what is the highest priority to run right now. And you can stop the current task to run something else. So the OS has the code that people like human wrote in to exactly figure out the policy on there. Yeah, and if you would like to take a look, I mean, you can definitely actually download the Linux kernel, and there are parts in the Linux kernel that is actually managed that. All right, so let's come back to our our class. Am I missing any questions? Because there are like 10 coming out at the same time. If I miss anything, let me know, please. Oh, okay, that's a great question. Would a function closure work between the two functions? Yes. Basically, let me put it this way. You can make it work basically because depending on how you define it, if you have function closure, it means that you might add some dependency. One more thing is you can still get parallelism benefit. It can still be run at the same time. The reason behind that is everything you do in the program, including function closure, a lot of those things can be analyzed by the compiler, right? So we've been talking about, hey, compiler is really smart. Compiler is actually a program that a human write. Again, right? We write a complex program to analyze your program. So when you have a function closure, the compiler can detect that and tell the hardware and the OS, hey, that's a closure right there. And these function closure require some variable here. If the hardware can detect that they are not dependent, they are something that's read only, no one will modify it, they'll run in parallel. They will run two functions in parallel. So to put things in the sense of if I want to put everything together, the way you write this program, when you put the word future, right? When you put the word future in Scala, it becomes a hint to the compiler. It's like, hey, I know that word. And I know that, hey, maybe I can do this thing and this thing in parallel. Because I know eventually I'm gonna get FIFO 45. For F2, I know eventually I'm gonna get FIFO 46. Then you detect that, okay, there's no data dependency. It actually tell the OS, say, hey, I spawn two tasks and you can do this in parallel. So you can write parallel program in Scala, but it's not as nice as Rust, which we're gonna move into. So Rust is a much faster. So let me put it this way. Scala is designed for functional programming. Rust is designed for both functional programming and parallel programming. Why do we choose Rust over Silk? Silk is actually as frank as I want to be. Silk is good, but Intel stopped supporting Silk. So I think they're trying to move on and come up with a better framework. So right now, if I would recommend something, it's either Go language or Rust or OpenMP. So maybe I should cover Go toward the end of the class as well. I'll see if we have time. All right, so let's come back to the discussion on the future, right? So assume F1 and F2 are defined. If you want to access the value of F1 and F2, because you know that, hey, someone will run this, and I don't know when this thing will finish, right? To check the value of F1, and you say, hey, I want the complete value of that. You say F1 dot on complete, and you do pattern matching. If you get success, results becomes your value. If it's not successful, you can handle that by pattern matching again, right? If success, you do this. If failure of E, this is the exception, you then handle the exception, right? Make sure you import this. Success and failure. It's a utility in Scala. It's a built-in API that you can call. Basically, it's used for pattern matching to get the value of your future. Right? So, any questions on how you can access the future? It's not okay. That's a great question. So, if you don't handle the failure part, will this give a compilation error? No, it will give an exception. If something fails, you get an exception. This is how you can access the exception. I do the pattern matching and say, in the case it fails, do this. The second thing is because this has something to do with time, right? Oops. So you have F1, right? It start here and it finish right here. And when you finish, you have fib of 45. You have fib of 45 right there. There's a state in the middle where you're still trying to compute fib of 45, right? So if you want to wait, for the future to become ready, right? This is what you do. You can say await dot ready. It will check if f is ready in the next minute. If f is ready in the next minute. Why is that useful? Why can't I say on complete? Right? Because earlier on I say, hey, if f1 on complete, I got the results. Right? Why do I have to have this? Await dot ready f1 minute. So these are some use cases. Let's say you have I/O call. You want to read something from your hard drive, right? These read in hard drive, it can take 10 microsecond. It can take 40 microsecond, right? It means that I'm gonna try to wait and see if it becomes ready in the next 10 microsecond. A function with long computation time, you might want to say, okay, if I wait 1 minute and it's not ready, I'm gonna queue this. It's too long, right? So that's another use case. You have long function and you can say, okay, if I'm still waiting for this, run other things. You can handle database query, right? This thing is long. Database query is taking minutes of your time, right? So this can be done similar way to the long computation, right? You do await, and if you got the data, you handle that. If you haven't got the data, you do something else. RPC call. What is RPC call? RPC is stand for remote procedure call. Let's say you have a server and you have your laptop, right? Your laptop RPC call to the server would say, hey, let's run this function on the server. This is the RPC call. You go through the network. So you can use the filter to represent the result of your remote procedure call. You can use it to force something to terminate. Okay. If I do this and I wait for 1 minute and I haven't got anything back, terminate. What is an example of that? Let's say I want to access a website, right? Let's say I want to access Twitter, right? And say Twitter is down at the moment. So I would do timeout. Say if I wait for Twitter for 1 minute and I haven't got a response, then I'll time out and do something else. I'll handle that somehow, right? Uh, there's also a concept called promises. What is promises in human language? What does it mean? Yeah. What do you tell? Like, let's say I promise you something. It means that I'm gonna do this eventually in the future, right? So it's kind of similar to the future, but uh, you can get the future with the promises, but not the other way around. You cannot get a promise if you just look at the future. If promise means that I'm gonna tell you this would happen in the future. It's agree between two people. I tell yes, it's agree between two people and say I will do this in the future. Think of this as how you handle real life promises. If you promise something to someone, you must keep the promise. Don't be a bad person. I want to say a different word. Don't be a bad person. If you promise someone something, eventually give that something to that someone you promised. If someone promised something to you, they should honor that in the future. If you say if you have a future, you cannot get a promise. You cannot force someone to promise you in the future. But if you promise someone something, you know for sure you get a future. So realizing future versus realizing promises, in so far is a good. Those are good ideas, right? So let's see how this is done in hardware. Because hardware, if you take architecture class, I'm gonna keep telling you hardware is stupid. You need to tell exactly how you handle each of the things. It's stupid. Uh, why should you care about this? Is because this kind of bridge the abstraction between the program language and how do you actually do this in hardware. And I kind of like ahead of time tell you how this is done. And basically, when you have future in Scala, the runtime say, okay, I can run this independently, so I'm gonna run it. So let's say I have CPU1, CPU2. It will the evaluate F1, which is basically future of of 45, right? While the CPU2 would then run whatever is future of fib 46. So this is how it translates to the hardware. You buy multi-core CPU. This is actually how this is being handled. The next thing is you can actually build the thread pool. What is a thread? I think I should have said that earlier whenever I use the word thread. The word thread means it's a part of your program that you're running. So a thread pool is a collection of idle threads that gonna go and get the assigned work that your program's supposed to do, right? The actual implementation of the thread pool will handle the creation of the worker threads and manage and schedule the task, right? This, to be honest, this is actually part of the OS, the kernel code. It will specify how this is done through the kernel. Some of the framework like OpenMP will have its own implementation to handle parallel. Sorry. To handle the parallel execution of your code. An event loop is in the system layer. An event loop is specified to handle certain tasks like file system, database systems, or web services. Uh, and please note that this rely on different implementation library and framework, so that each of them will propose different things. They have different trade-offs. Some will be fast, some will be slow. So I do have an example code here, so let me put this up real quick on the thread pool example. It's actually done in Rust, and I'm gonna show you in a bit here. So you see my screen. I will not actually let me. Do you mind if I talk about Rust first before we go to this? Because this is done in Rust language, so I don't really think it's a good idea to talk about it now. Okay, so let's wait until we talk about Rust. Let's talk about how do we unblock them using future and promises, right? Using future is basically you allow pipeline program execution. So this is software pipelining. If you're in my architecture class, we are talking about hardware pipelining. Same concept, different application. This is software pipelining. Pipelining means that if I have tasks that can be broken down to subtasks 1, subtask 2, subtask 3, what you can do, and let's say you have n tasks that looks like this. It means that the first subtask would finish and basically run that and finish, right? You move subtask 1 to subtask 2 for the first job. Then at the same time, you can start subtask. So this is job 1, job 2. Then you can start the subtask 1 at the same time as subtask 2 in job 1. Basically, this is why we call it pipelining. You move the task in the pipe, then you put in the next job beginning phase so that you can do things in parallel. So let's go back to our example earlier, right? Here, where's my mouse? Here. Remember this example from, let's go get a HTTP website and figure out the keyword. And I told you, right, that this can be done in parallel because these three things have nothing to do with each other. So let's do that. Let's utilize future and promises. And here is the code. Notice we use the future here. Now your sequence is a string and future. Basically, the future will now, I'm going to keep the highlight because that's where you can see the word future. So what are being parallelized? What are being parallelized? Based on the code that you see here. So you will process all the 4 websites at the same time. Basically, that's the key. You want to process all these 4 websites, right? The website Wikipedia, Scalarlang, Apache.org, and yeah, you basically do the count function all at the same time because each of these websites has nothing to do with each other. It just run the same task but with different inputs. So what you do here is this is the sequential version. You do just counts equal future of vector of int, right? So it's a future of vector of int, and you traverse. So this is a built-in function from the future libraries. It actually go through the first list in the web URL, which is this, right? Apply this function. Apply this function in parallel. Then the actual count, right? Now you have the future. Basically, now you have the future of vector of int. The vector of int represent how many times the word the happen in each of these 4 websites. How many times does it happen in the Mahidol website? How many times does it happen in Apache.org website? How many times does it happen in Wikipedia website? When you have that, the actual count, you basically say, hey, I don't know how long this count would take. So I'm going to wait and check this every 10 seconds. So if it doesn't, so over here, that question is great. So if we wait 10 seconds and it doesn't return what happened, over there, it terminates. Basically, you stop, that become a failure. Remember, future has success and failure, right? If you have 10 seconds after this and you do something with the data at that point, it's still not complete. So you don't get the success. All right, so let's do a quick break before we do a group exercise. Actually, the group exercise is another piece of code that I will basically ask you to check what the code doing. The code is right here. I mean, unless you want an individual in-class exercise, basically this is kind of like right before your midterm. So everyone here, I will go through this with you. Basically, after we are back, we'll go through this code with you. Maybe maybe I should put this code on the canvas so you can take a look while we're taking a break. Is that okay? So the file will be called lecture 6 in class exercise.scalar. You can look at the code while we're taking a break. Let's meet at 11:40. Is that okay? Basically, it's like 17 minutes break. Okay, so let's meet at 11:40. I'm gonna put this on the canvas so you can check out the code, and we'll meet at 11:40. All right. All right, so let's wait maybe a couple more minutes. So hopefully most of you are back. All right, so if you have not had a chance to go through the code here or look at the code, please look at them with the two main questions. What is the code doing and what is the future used for? Uh, over here, future is used with a lot of things we discussed previously. So you see a lot of example in the code that you see right here. But the first question I would like you to try to answer is what is the what is the whole thing try to do? I'm gonna skip the top part right here because those are basically libraries that are related to dealing with HTTP and dealing with future and dealing with parallel programming in Scala. So you import those things so you can use it. What do you import? Things like await that we talk about. What are the exceptions that would have to happen if you want to cancel, right? If you want to cancel things you're running. And then future and promises. Basically, future and promises, right? And here's the main part of the app. Notice how there's a try catch right here, right? And you get the HTTP client. So I'll give you maybe 10 minutes to check out the code and then we'll ask a few questions about what the code is doing. We'll go through that together. And if you have any question, list them here. I'll answer them while I'm eating my lunch. I'm sure you're all kind of like getting lunch, eating lunch as well. So feel free to use that time to kind of like eat and look at the code together as well. All right, so yeah, there you go. I'll start asking question at 11:55 probably. The main two things I want you to answer are what's the code doing and what is future used for. There's also promise, so that's kind of grouped in the second part. the UI, it actually should be replacing this part. So you can do this. Yeah, my bad about the code. Suddenly have an input that never get used, and then I retype the website again in there. To be more precise, it replaces this part, actually. All right, so I assume you have seen the code quite a bit. Anyone here want to take a stab at what the code is doing? Yeah, you got it correctly, actually. It, yes, yes. So let me break this. Someone call. Give me a minute. I need to respond to this. All right. Okay, so that's actually what the body is doing. Basically, this part in particular, this part is basically you get the HTTP, right? And you basically have the input. So this is the beginning part that I have. So this is basically UI, but essentially it's the same thing. You establish the client. Yes, exactly. And then you return the top five most used words in all the websites. So you go to the website you put here and you create a new HTTP client to get the response, from your request. You visit, hey, I have the URL. I want the HTTP response, which is the website. You have this whole block of code, right, here is along the line of like, okay, whenever I request a website, sometime it doesn't give me the website, right? You go to Twitter, sometimes it's slow, sometimes it doesn't respond. For whatever reason, you don't get to access Twitter. Then it will be fail, right? So when you have a failure here, in this case, you return the promise failure, which is basically I cannot access the website. If someone cancel, then you raise a new cancellation exception. Otherwise, you return the website. So this is the big block is for. Once you have that, basically the rest are parsing. It parse all the tokens. Once you have all the words, you put that words in basically into a list of words that you've seen so far, right? The list of words it has certain lengths. Then you map the whatever tokens you got, you map it, and you do sort by, right? Sort by the first input, second input. This is the order, and you reverse to get the, instead of from lowest to the highest value, you reverse to get the highest to the lowest. And then you take five, the dot take five basically means I'm going to take the first five sorted from most frequent to the less frequent. After you got the parse future, and you await. The await function, basically, I'm going to wait 2 seconds. I don't know how long the website is, but within 2 seconds, I'm going to get the top 5 most used words I've seen so far. So if you go back to this question, what is the future used for? What is the future used for in this case? It's actually used for establishing the HTTP connection. It has a promise that if this doesn't fail, it promises that eventually you get the website. Otherwise, the await function within 2 seconds, if you haven't got the website, just parse whatever you got so far. You might have parts of the website, or if it's failure, then you will not get it. You're gonna get an exception. All right. Any question before we move on to parallel programming? Okay, so let's switch the topic and move on to parallel programming. So if you have taken the OS, you might have figured out that system programming and parallel programming can be annoying. It can be annoying. System programming, for example, is hard to secure and hard to multi-thread it. Parallel program is also hard to detect data race. What are data race? Data race are, oh, okay, so we'll talk about that at the end of this class. If you are not in the lectures last week, then next week is the midterm. And that's the only midterm we have. So we have one midterm, one final. Basically, next week will be an exam. Anything we cover so far except for this class, lecture 1 through 5. I think this is lecture 6, lecture 1 through 5. Then once we talk about parallel programming, that goes into the final. Okay, so let's talk about parallel program. It's hard to detect data race and hard to debug. The reason why they are hard to debug is because there are multiple things running in parallel. And let's say you have a bug somewhere. Whenever you have the bug somewhere, every time you run this, depending on the speed of each thread, you see different things. If thread 1 somehow is faster this time you run it, you see certain inputs, certain data. If thread 2 this time you run it and it's faster than thread 1, then you see a totally different data. Those are possible. Right? So it's hard to debug and hard to detect data risk. There's a benefit in using a language we call Rust. The first one is type safety. It's a well-defined program. What is a well-defined program? It means that there's no undefined behavior under any case of our execution. Basically, you run a program, it's well-defined. There's not going to be some weird behavior. It's a type-safe language similar to Scala, where every program is well-defined. Is C type-safe? Oh, is C type-safe? I would like to ask you that. And if C is not type-safe, why should we use C? What's the benefit of using C as a language? So let's go through the first question. Is C type-safe? Yes, and you guessed correctly. That's not type-safe. It's a type conversion that C would done implicitly without letting you know and give you warning, right? You've seen all the warnings about like when you are in a system skill class or file processing class, when you use C, how many of you run into warnings and you're like, I'm gonna ignore the warning and I hope, pray that the code runs correctly. Yes, and it's not exactly type safe because some weird thing can happen with those like implicit conversion. The warning that they're giving you are hints that, hey, I feel like something is wrong here, but as a language, I kind of know this is what I would try to do. If something bad goes on, your fault, not my fault. This is the warning. That's for the warning. Uh, Yeah, so what you do in the class assignment, you usually I ignore the warning, cross your finger, run it, and hopefully you got the results, right? In reality, I would definitely suggest you check the warning if you know exactly what they are and you know that that's safe, it's fine. If you know, check the warning, you know that warning is weird. I did not intend for that to happen. Maybe you should go and check it out, right? Uh, then why should we use C? What's the motivation behind using C as a language? What do people tell about when you're telling people, hey, I use Python, and you might see some like hardcore nerds who say, hey, no, Python is for the weak and you should use C. What is their argument? Or if you prefer C, what is your argument to convince your friend on why you should use C? Any any suggestions or any comments that you got from your friends? Yes, one of the good thing about C is definitely not aesthetic. C code looks a little bit more ugly than Python in my opinion. But if you have small resource requirements, you can use C. The reason behind that is C is low level. It have a lot of control given to the programmer. So you can optimize your code, right? Uh, so you can somehow cramp things in. If you assuming that you know what you are doing, you can optimize your code quite a lot because C give you all the control that's super close to the hardware, right? It's not as close as assembly, but it's close enough compared to Python or Java. Not exactly. See, so the comment is like Rust tell you the errors. C also tell you errors. How many times you compile and fail, right? In system skill or file pro. So C also has the benefit of telling you the errors, but C also give you low level control. And the reason why C is good in certain scenario, I'm not saying it's good overall, but performance is king. This is how important writing fast program is, right? And this is a so let me stress this because I don't think this point gets stressed enough in the programmer community in Thailand, actually, because many people assume that these days the hardware are really good. I'm gonna write some inefficient program and they would run. And yes, that is true to some degree. But if you can get more performance, let's say you want to uh, make a search engine, right? What if I can tell you I can come up with a search engine that is faster than Google, but is as accurate, as accurate as Google? Somehow that seems like a good option to use as a search engine, right? So the more performance you get out of your software, the more user you can attract, right? And this performance differ across languages. The reason behind it is depends on how much control you have over the hardware or over the low level things. Uh, there are additional lines in assembly code that's built in when you have things like Python and Java that doesn't give you a lot of control. So it's not, it can be inefficient. Computer, the way they execute, actually execute assembly code in binary, ones and zero, right? And somehow the language, whatever we learned so far about the computer language, translate your program in English into assembly code into binary. And we haven't even touched how hardware can vary, like the CPU and GPU. If you take a CPU code and throw the GPU at that code, I can guarantee you performance will suck because you have to think when you use a different hardware, you have to think before you program. Uh, so let's compare some basic program and see how performance differ across different language. And the program is I'm gonna check a string and I would return true if the string only consists of white space, things like spacebar and enter, the new line. And here's the code in Ruby. Right? Ruby is one of the scripting language similar to Python and it's old. So here's the code. Basically define blank if it's blank, return true. And you can basically if you run this, you can run 964,000 of these code within 1 second. So basically, I look at my clock, measure how many times I can run this in 1 second. So it's about 1 million of this per second, right? Let's look at the C performance, right? The code here is kind of cite the source code is shown right here. I'm gonna show you the C code. And as you can see, this looks extremely ugly and it's hacky as hell, right? It's really hacky. You basically have the input string, right here as an input. You convert that using pointer arithmetic, somehow force a string into a bunch of character. If it's uh, based on the location of the string, you then force force to encode these things compared to switch case to make sure that it compares to the white space and return, right? And return. Uh, and that's pretty much all for the code here. You can then, you might have realized this is really, really, really optimized, but ugly, right? And you can run this 10 million iteration in 1 second. This is actually 10 times faster than Python, right? So this is performance in C. You can optimize and you can deal with binary directly, and you can kind of like hack it such that your code is fast. So if you do this in Rust, here's the code, fast blank. I'm gonna slowly break this down. Basically, in Rust, you can define a function using fn. Fn is similar to def in Scala. It's a function. Take in one variable that is a buffer type. Return a boolean. You slice them. Get the iterator for all the character in my string. It's a function that now compare if this is white space. Right? Buff.addSlice, get the slice in the string, slice it up to different character into a character, and you iterate over each character. The rest is check for white space. And somehow you can run this 11 million times per second. This is fast, right? This is fast. So the code looks not as bad as the C code, but is perform equal to what the C code version perform, right? So here is why Rust is good. If you want to do parallel program, let's say I want to load any images from my input path to all the images. And don't worry about the syntax here. We're gonna learn how to use Rust in the next lecture after the midterm. I'm gonna show you some sample code. Today, my task is to convince you to use Rust. My task is to convince you to use parallel programming and use Rust, and maybe, hopefully, feels like maybe I should write the program faster using parallel programming. So here's the code that load the image, right? Here, path.iterator give you iterator. What is iterator? Basically, is a object that allows you to iterate over different elements of your collection. Over here, the collection is a different part in my computer. Then you load each image, right? And then you create and return the vector image that you loaded. And note that this is sequentially done. Nothing here is being parallelized. This will run and this is done sequentially. You have different path. Then you load the image given the path. And you realize, right? If you have a folder, let's say it's this folder or your path, right? You have multiple images that have nothing to do with each other, right? So can this be done in parallel? The part that load each images and put the data in my return array. Can this part be done in parallel? Yes or no? Are there dependency? Do I have to wait for the first image to load before I load the second image? No, right? You can just load all 5 images in parallel. There'll be no problem. So you can do this in Rust. If you want to parallelize the code earlier, the bold part are the things I added. There's a library called Rayon, right? Rayon allows you to parallelize your Rust code. The only difference, instead of path dot iter, which is serial version of your iterator, you change it to parallel iterator. This would perform the loading in parallel. It gives you an iterator. You go through each element in parallel. So Rayon is a data parallel library that converts sequential execution into parallel execution. And if you're curious, we will talk about this more, like way more going into the next lecture. But here is the documentation for Rayon and how it works. The link is provided here. Okay, that's a great question. So the question is, what if we apply par underscore something to something that's not parallelizable, right? It would detect that you can parallelize them. There are certain properties that you can directly tell if certain things are parallelizable or not. One of them is if the thing you are trying to access are read only, no one modify the content, those are parallelizable. Because everything looks the same. No one is modifying anything. There's no synchronization point. That allows you to parallelize things. Otherwise, you have blocking. So is it possible? Yeah. Is it fast? No. So path.par iterate over each of these paths in parallel. They'll do at the same time. And as I said, we'll go to these detail later. Another benefit is detecting data risk. So you remember the ATM example where I have a bank account, right? And depending on who arrived at the ATM first, you want to make sure everything is done in the order of arrival. Otherwise, you have the problem of data races, right? It basically each thread race to get the data, and whoever got it first break everything. So Rust compiler will tell you if you have data races, right? If you look at this, right, and you say, okay, I have multiple images, I'm gonna load them. If the file ends with the JPEG, I'm gonna load that into my path and collect it, right? The dot collect will count how many JPEG are in there. My bad. The collect part, this collect the image vector, and this part will update how many images you have loaded, right? Because you modify, basically this is how you detect and fix data races. Because you modify JPEG, right? It's the mutable variable, right? The keyword let over here, the word let, which I see here, it binds JPEGs, the name, to a variable, 0 now bind to JPEG. And you say, hey, JPEG can be modified. This will not compile in Rust. It actually detect the data res for you. And I'll tell you where is that data res. You notice you have parallel iterator, right? You want to do this in parallel. And here is the data res. So let's say you have JPEG. Let's say image 1, 2, and 3. Right? You want to load 3 images from that folder. Image 1, image 2, and image 3, right? So this is thread 1. This is done for using thread 2, and this is done using thread 3. Data res means that I start with this variable at 0. It just happened that thread 1 over here got in here, JPEG is 0. This is essentially JPEG, right? equal JPEGs plus 1. So you know that, okay, this is 0. I'm going to add them. I'm in the process of adding them. Right? Thread 1 is here. Is in the process of trying to add 1 to JPEG. Suddenly, thread 2 also arrived into this line, right? Thread 2. And at that point, thread 1 have not finished. It has not finished writing to JPEG. So JPEG is still 0. Thread 2 also see that this is JPEG is 0. So you have data rest, right? Both of them see 0. You add, you have 1, you write it back, JPEG becomes 1, even though you just read 2 images. So with this, at the end, JPEG will equal 2 instead of 3. Right? This is not correct. The way to fix this is you need to define JPEGs and bind this to atomic operation. I'll talk about atomic operation a little bit. Basically, you want to lock this. Right? You want to lock JPEG. Whenever someone modify this, lock it. This is the data type. It's unsigned 32. It's similar to unsigned integer, but you tell them it's atomic. Atomic means that it's the following. What is an atom? It's basically it's the smallest unit of things, like of the matter, right, in the universe. And okay, so the question is this shared amongst all threads? Yes. If you look at this, JPEG is shared amongst all the threads, and you parallelize them, and you have data races. Right. So atomic operation is essentially an operation that has to happen all together. It's either happen all together or this never happen. Right. So if you have this thread 1, thread 2, and thread 3 earlier, and you want to do JPEG plus equal 1, right? This whole thing has to happen and finish. Otherwise, it would behave as if you haven't even started adding 1 to JPEG. If you say this JPEG has the type atomic unsigned, it means that if I want to do plus equal 1, I will finish that before someone else can modify or read the data. Why is it useful? It gives you the synchronization that you need to lock that variable. It gives you the synchronization substrate that allows you to lock JPEGs. It tells the hardware, if someone else tries to modify this value while I'm modifying it, it's either I fail my rights and I have to redo that, or that person will need to stop until I finish. Is this similar to committing your data before allowing the next read or write? What do you mean by committing your data before allowing next read or write? Like, can you define commit? Because commit can mean multiple things here. Oh, so basically it just means that the whole sequence of modification to atomic variable has to happen before someone else can access that variable. I'm gonna get it. I'm gonna lock, kind of not really lock it, but if someone else modify it before I can, I'm gonna behave as if nothing happened. It's think of it as this. If you want to be a thief, sneak inside someone else's house and you want to be sneaky and modify something in the house without that person knowing, you want to behave as if the whole operation succeeded or you never in there. Right? I hope that analogy is making it a little bit more clear. So now let's talk about how to read Rust code before you can write Rust code. Fn defines a function. For example, fn gcd, it means that I'm gonna declare a function. I'm going to break this code down one step, but basically one step at a time. Mutable, right? Over here, you say, these are the input variable. It's mutable. You can modify this n and m. The type is unsigned 64 bits. This is a macro assert, and then the exclamation mark is assert only false. Otherwise, without the exclamation mark, it assert if true. Notice the return type of my function. You need to tell the return type, right? It's a well-defined and well-typed program. No parentheses in the condition check over here is okay. You don't need the parentheses. It knows that, okay, this means that if m is not 0, do this. Notice you have a loop. This is a little bit easier than Scala where you have no loop. This is like a better functional program. Like it's more easier to program because you have a loop. You can use the while loop. This let create the local variable. It works inside this function closure, so it knows the scope of this is between this and this. So t will be known in this range, and outside of it, that's it, right? Type can be inferred. If you do let t equals m, it means that t will take the same type as m. And then you can also type return n at the end. Otherwise, whatever is the last line before the end bracket, that's the return value. It's similar to Scala. Any question on this page so far? Okay, so if you have no questions about this page, let's talk about generic types. Because we had that earlier in Scala, and this is the same thing. You can use parameter for generics. Basically, this tells that this T is an order type. An order type, right? It need to have total ordering. What does it mean to have for something to have total ordering? Oh yeah, so the question is U64 is any data type that is 64 bits, right? No, actually U64 is stand for unsigned int 64. My bad. It's unsigned integer. So U64 means that it's an unsigned integer that is 64 bits. It's an int. Yep, it's unsigned. It starts from 0 to 2 to the 64. I'm into the 63. 0 to 2 to the 63. So order means you have total ordering, which means you can sort them. There'll be an order between the first to the last elements. Every single element can be compared, and every single element in the whole thing as a collection can be sorted. What I do here is if A is less than B, else we return A because you want to find the minimum value of the two elements A and B. The type has to be order. Basically, you can have an order between the two inputs. Otherwise, you cannot find the minimum of the two number, right? So the next thing I want to talk about, because we covered this in Scala, is you have enumeration and sum type. Enumeration is something like this. If you want to define the sum type like an option, you can say this, enum option of t, right? And it has two things, none or sum of t. For example, if you want to use an option, you can do this. Option in the bracket, I32. This is int 32 bits. If you use I, this is int that has the negative and the positive side is a signed number. U means that it only has a positive side, unsigned number. Numerator and denominator, both unsigned, both are signed bits, 32 bits long. If d is 0, it means you divide by 0, so you return none. Otherwise, you return sum of n over d. You can then do pattern matching, right? It's safe division with this function, right? The function you called earlier here. If you get none, it means that there's no quotient. Otherwise, there's a quotient, and the quotient is v. This is basically pattern matching. It looks almost like scalar. And you can then extend this concept of the sum type by trying to do error catching, right? This is used with results. This is almost like an exception in scalar. Basically, you run something, you either have the result or some error message, right? So let's use this to print the content of the directory and return the number of entries. Otherwise, there's something wrong with our code and it cannot access that directory. It gives you an error. So here's the code, right? Let's read this one at a time. Let's read this one at a time. These are the codes. You have the path over here, right? And from the path, you want to list the directory in the path. So you do pattern matching. You do pattern matching. You either got an error or a number of directory. Number of directory. This is the function, right? The function counts the number of directory, and based on your input directory here, you start count at 0. Notice how I have the mutable variable. Don't forget that if you want to modify something, some variable, make sure they're mutable. Let bind the count, the name count, to value 0. Then you try this, right? Try to read the directory. If you cannot read it, give the error, right? Otherwise, you count this by 1. If it's a directory, you count up. If there's something wrong with how you read directory, you then spawn an error so that you can catch it down here. So this is how you can do pattern matching and use option and sum type. The next thing I want to tell you, my cat is going crazy. The next thing I want to tell you is Rust gives memory safety. So how many people is bored with segfault? How many people love segfault for some reason? If you want to go crazy and you love segfault, I don't think anyone loves segfault, right? Including myself. I hate it when I received it. I was like, oh my god, what did I do wrong here? And so I need to use GDB to debug my code. If you love segfault, you need to talk to someone. Something is wrong with you. Anyway, Rust provides 3 promises. There's no null pointer dereferencing. There's no null value. You use option and you use result, right? So you don't have to deal with the first potential segfault when you have to compare things if it's null or not. You do pattern matching. If the type doesn't match, the compiler detects that. It is almost as if you write a program and instead of running it and run into segfault and you have no idea what caused the segfault, now the Rust compiler will tell you this line will cause the segfault. It will not let you to run. It will have a compile error, but the message will be telling you how to fix it. The second benefit is there's no dangling pointers. There's no dangling pointers. So, what is a dangling pointers? It's basically a pointers you define and you use it sometime and you don't use it some other time, right? This is pretty dangerous if you don't know what you want to do with the pointer, because sometimes you can reference the pointer by accident and again, segfault. So there's no dangling pointers. You don't have to worry about what is the address that my pointer is pointing at. Can I access it? There's also no garbage collector. If you use Java, if you use Python, there's this thing called garbage collector. In C, what you have to do after you do malloc, let's say you malloc temp. What do you do afterward when you are done using temp? All right, I think there's a delivery guy coming into I have a package. So let me take this call because somehow they don't know where I live. All right, so garbage collector is when you malloc, you have to free. That's correct, right? So afterward, when you're done using, you have to free. What happens if you forget to free? What will happen if you forget to free your allocated variable? You are going to run out of memory. At some point, you run out of memory and your computer will be super slow. We call this memory leak. If you use this tool called while grind, it can help check for these bugs. In Java and Python, instead of malloc and free, you don't have to do that, which means that there's actually some entity that goes check all the allocated space for your variable and free them. This is called garbage collectors. And whenever garbage collector is working, it basically it pause everything. So your computer becomes slow for all of a sudden, right? It would freeze up and become slow for like half a second. So you notice like something is pausing. So that can be annoying to performance. In Rust, there's an ownership system that directly tell when things can be free. You don't have to malloc and you don't have to free. Rust detects when free has to happen and will do that for you. There's no buffer overrun because there's no pointer arithmetic, so you are not going to by accident go out of bound in your array. Array in Rust is not exactly translated to pointers, and there's also boundary checking when you compile your code. This means that you're not going to run into things like segfault. It also means that if you write a code that are risking something similar to segfault, Rust will tell you what happened. If you now read the error message, it's actually more telling. It will tell you what is wrong. So you can identify what's wrong and fix it. So now this is a really easy in class exercise, and I won't check it. There's no score with this. My task is install Rust and try it out. Write a program to print hello world. Make sure you have it installed so that when we meet after the midterm, you have Rust installed and ready to run code. So the way you install Rust is basically Google Rust language. It would go to the website that has an installer. You use that. Hopefully you can run Rust code. If you cannot, let me know. All right. So that's it for the content of today's class. Right now, let me proceed into some for like is there its own IDE? Let me check for you. Let me check that for you. I think IntelliJ might be able to work with Rust. Uh, let me check with your senior students. Won't we have class on next Friday? Yes, we will not have class next Friday. It's a long 5 days exam. I will tell you about that. We talked about the exam format since last week, right? And that's the reason why I give you 5 days. It's not going to be a long exam, but because it's a long weekend, I want you to enjoy the weekend. So I will give you the flexibility of when you want to do the exam. So before we go through that, let's go through some review. So these are topics we have covered, right? Make sure you are familiar with these topics. If you have any questions, there is a makeup class for the next week uh, at 2 different days. So I'm going to be online. You can come in and ask questions related to these topics. You can ask questions after we talk about the exam format as well today. But basically, the first topic we talked about, the first thing we talked about in the class are the evaluation rules, the substitution model, termination. Remember our old friend Lou, right? That never finished. We talk about evaluation strategy, call by value and call by names. We talk about conditionals, if else. So these are the first lecture. A second lecture, we talk about recursion. We talk about tail recursion. We also talk about what to do if we want to have recursions that call a different function than that function called the first function. We haven't. It's a fair game if I ask you to implement something like that. We haven't had an example on it, I think. So I will limit to things like extra credit. Basically, it's a function that called another function which called the first function back. So we talk also about the compound data, list tuple, and how do you make your own compound data? For example, how do you make a tree? We talk about class with objects. Notice class is not singleton and object, but object are singleton thing. We talk about options, and then we talk about sum types, the product type, and records. We then talk about pattern matching, right? We use pattern matching a lot after we talk about this topic, right? All the in-class exercise has pattern matching some form or another. We talk again some type, polymorphic types, where types can change based on a different time and instance. We talk about exception. We talk about interaction between different functions, how you can pass function ins and return a function. You talk about forwarding and mapping and closure and the scope, the lexical scope and dynamic scope. We actually went through an example with a lot of like variable defined, and we can ask you what's the value of that line of that variable and it defined in that line. We talk about continuation and we talk about currying. Okay, so that's the last topic. Currying is the last topic that can go on to exam. Anything else will be on the final. If you have any questions, feel free to kind of like collect all your questions and ask me so that we can go through that before we start the exam. Now that I talk about topics we have covered, I really want to talk about this before we are done and go through the midterm, because this is something dangling that you have to do, are the projects for the class, right? So there are things that you could obviously do. For example, if you learn certain data structure from the data structure class and learn some algorithm from that data structure, you can do that in Scala or Rust or Go or any parallel programming languages. Right? Say you can insert, look up the red black tree, or you can perform like a graph search or graph coloring with different data structure. How do you represent the graph? There are multiple ways you can represent the graph. There are a method to do for a sparse graph. Then there's another method for a dense graph, right? For example, if you want to do contact tracing for COVID-19, right? This is totally doable in parallel program using graph, right? So these are actually viable projects. I will tell you what's my expectation so you don't kill yourself finishing up the project. But if they are too easy, I will also tell you what you might want to add to make it as hard as your friend's project, right? And I'm aware of how much time you have. Please, please, please make the idea interesting. I want you to be motivated by what you want to implement. Make it as interesting for you as much as possible. If you don't have a good idea right now and you want some suggestions, let me know. if you have projects in the other classes that you're taking, feel free to write a parallel version of that, right? But these topic maps well with, this class is now called Parallel and Functional Programming, not OPL. But many of these projects or assignments you learn from the other class, it it maps well because you can write the program to make it scalable or to make it faster using parallel programming, right? So if you took database class, if you somehow took the parallel algorithm class, there was a student last semester who actually implement what he learned from the parallel algorithm class in Rust, right? And then do merge sort uh, in parallel. And the merge sort as a result is really fast. You can play with Scala. You can play with Rust. You can try out OpenMP. You might have heard about this. This is like a parallel programming framework that allows you to utilize multi-core. You can try out CUDA. So if you have heard about TensorFlow, how many of you heard about TensorFlow or PyTorch? So you can play around with that too. TensorFlow and PyTorch are more like an APIs for machine learning. So if you have to work with TensorFlow, maybe if you want to kind of like merge that into your project for this class, we should talk because essentially what you have in TensorFlow are really, really data parallel program that can be run on GPU. GPU is really, really good at running things in parallel, but they have really strict restriction. If your program doesn't follow that restriction, it will be super slow. It's like a lot slower than the CPU. So you need to. A lot of people use then PyTorch or TensorFlow to automatically parallelize things for you. So if you take, I think deep learning, right? I think there's a class on machine learning right now. So if you're taking that class and you want to kind of like adapt the project that you do over here for this class, let me know. And those are interesting options as well. And I think you would learn a lot without killing yourself to finish the project because these days there's so much support to program these things. All right. So there are also more on Rust. If you annoyed about concurrency issue in parallel programming, you can deal with certain things in Rust, right? Uh, so the reason why we actually introduced Rust to you and you can actually try it out is you can get performance and it's safe and it's syntactically it's kind of similar to C++. So you used C++ before. Feel free to play around with the project idea in Rust and obviously, as I said, you can write parallel program that would run on the GPU. For those of you who like challenges, you can do things like matrix multiply in GPU. Why do I suggest matrix multiply? Every single machine learning model relies on matrix multiply. How many of you watched the iPhone 12 introduction video? All right, so if you watch it, you might have realized they have this thing called neural processor. Remember the neural processor they put on the iPhone? That thing is designed to do matrix multiply. I can tell you that. Yeah. It's a chip that is designed to do block matrix multiply. The way they designed it, if you're interested, I will try to cover that toward the end of the computer architecture lecture this semester. So if you're interested, let me know so I can share you the link to the lecture. Yeah, they want to make linear algebra stuff, which is essentially matrix multiply. They want to make it faster. And yes, they put a chip in. Right now, the way the research go, for example, I have a project under submission right now that perform matrix multiply inside the memory. Right? So you don't have to have a special chip. You can do that inside the memory. And the way they do it is actually follow physics. I multiply by V, add them, and you got the results. So these kind of idea are being proposed in the architecture world right now. So I think in the next like 3 to 5 years, you'll see a lot of like improvement in this kind of chip actually. I mean, I saw it already in the iPhone, for example, and I think I've heard like most company, Google has Tensor Core, right? Same thing. The Tensor Core is designed to do matrix multiply. Uh, I'm sure all the companies that has someone in hardware, they are building this thing. Alibaba, Huawei, Samsung, they are looking into these things as well. Another project that you can do for this class is if you want to play with language and compiler and let's say, hey, let's introduce new things to the language. You can use this thing called LLVM and you can modify how the compiler treat your code. But be warned, this thing is probably the most complex of all the options I list so far. So if you want to go this route, definitely talk to me and Ajahn Kanat, both of us, so we can actually structure it so that you can get something really, really beneficial. But this is more like a senior project level. Uh, so hopefully you got my message. You can do this as well, but if you want to tie this to your senior project, let me know. Before we leave today, next week plan, as I said, I listed multiple topics, right? So we will cover Q&A during this class. By the end of this class, if there are more questions or if you come up with more questions afterward, we will start from October 20th and October 22nd from noon to 1 p.m. I will be on WebEx to answer the question. So you can come in. These are not mandatory, but feel just treat it as an extra office hour that you can come in. But I will do this on WebEx so I can record it, so I can post it on YouTube so that you can watch if someone come in and ask questions. If it's just a session with me alone, no one comes in, then there'll be no video. I'll let you know there's no video because no one comes in. There's no more questions. So good luck on your exam. Uh, Exam format, as I said, is take home with all material up until currying, not up until now, up until currying, which is basically the last lecture. And because it's a long weekend, that's right. It's a long weekend next Friday. I don't want your life to be miserable. So I'm gonna release the questions right after that office hour on Thursday. The question won't be before that. Otherwise, you can come in and ask the questions. And you have 5 days, basically 5 days coming from that release, which is 1 p.m., October 22nd. To finish it, the length is the same as if you're working on a 24-hour exam. I will not expect you to work over the weekend. Please, please, please go and enjoy your vacation or do whatever you need to do. This exam should take no longer than a few hours. It's designed for a 24-hour period of your time. Open everything and I'll be online in WebEx. At some point, I again still need to figure out my schedule. I will announce the time next week. If I cannot find a slot, I'll be on Discord. It's just one way or another. I'll be online for about 2 days. And yes, assignment two. Originally, I intend for that to be due on 23rd. I already pushed it to the 26th because I know you have the long weekend. So yeah, deadline will be on the same day, October 26th. Please manage your time. And you can use late days. You have a few late days. I going to be on Discord after this. So after 2 o'clock, I have another meeting with like the team at National Taiwan University. So before two, yeah, I'll be on Discord. Yes. Yes, you got 5 days to complete the exam. That is designed for only like a 24-hour exam. please manage your time. I'm giving you this flexibility because I don't want to murder your weekend. I don't want to force you to work on the 23rd. I don't want you to force you to work on the 24th or 22nd. I give you an option to pick the day you want to work on it. And I'm sorry to have to release it during the long weekend, but so many long weekends this semester because of the government. I don't know why they make that decision, but there's so many long weekends. So one way or another, there'll be conflict with the class. So yeah, so that's that. This is kind of like, I guess, the end of this lecture. I'll move on to Discord and I'll do a Q&A over there on the topics we covered so far or anything in your in-class exercise. Let me stop recording here so we can move on to Discord.